Okay, let's start now. Hello, everyone. Good afternoon, or maybe good morning or good evening. Thanks for listening. I am Jielong Zhou from China, and I'm a software developer of Ant Group. I have been developing DPDK-based application for several years, and in the last 2 years, we are developing and applying a DPDK native network stack named TLDK v2 in cloud-native environment. During the development and deployment of TLDK v2, we found in some aspects that DPDK does not meet the requirements of cloud-native environments very well. And we made several modifications and extensions on DPDK to make it more cloud-native. This topic would introduce a part of this work. My topic today is dynamic mempool, one of the final steps to make DPDK cloud-native. It's our experience on how to extend the mempool library currently in DPDK to make it more lightweight and elastic to meet the requirement of cloud-native. At first, let's take a glance at our application scenario. TLDK v2 is a DPDK native TCP/IP stack for user space. It's developed and open sourced by Intel and Ant Group together. My colleague Jianfeng and NAF Constantine from Intel have introduced it in last DPDK summit. TLDK v2 supports POSIX compatible socket interfaces and necessary network protocols in layers 2 to layer 4. Therefore, it could be easily integrated into applications without major modification. And we use it as a network stack of an application kernel, which would run a lot of different applications in cloud-native environment. When we were trying to deploy TLDK v2 in cloud-native applications, we found cloud-native applications are quite different from typical DPDK applications. Cloud-native is a quite complicated concept, and we are not about to analyze it here. Instead, we summarized some different characteristics of cloud-native application and typical DPDK application we saw. Typical DPDK applications normally process network data with high bandwidth and high throughput, but the load and throughput of cloud-native applications varying from each other. In most times, the network loads of applications in cloud-native environments are quite low, but in some point of time, it would grow dramatically. And a typical DPDK application would be deployed on a server with just single or very few instances. While in cloud-native environment, there would be many instances of different applications deployed on a single server at the same time. The number of instances on single server could reach 100 or even more. And the life cycle of cloud-native applications would be much shorter than the typical DPDK applications. A cloud-native application instance may exist for several days, hours, or even minutes. Another major difference is the usage of memory. Typical DPDK applications normally reserve enough pages memory and initialize resources for worst case at the initialization. But cloud-native applications need to use memory elastically along with their load. At last, cloud-native applications need to start up and initialize quickly, but typical DPDK applications don't care about initialization time and memory cost very much. From above comparison, we could find cloud-native applications are quite different from typical DPDK application. And currently, DPDK could not meet all the requirements of cloud-native application or environment. And the mempool library is one of the main issues and would be the main topic we'll talk with today. As we all know, mempool is a fundamental part of DPDK, and many important libraries such as RT-mbuf, RT-ethdev, and all device drivers are developed based on it. So it's hard to replace it simply with a totally new library. But currently, mempool library doesn't support allocating resources and objects dynamically. DPDK now do support dynamic memory mode, but it only supports dynamic memseg allocation. But as a network stack of cloud-native applications, TLDK v2 consumes varying numbers of resources over time. So concurrent connections may grow when the applications are accessed by more users, and the need for mbufs and other resources may grow simultaneously, and current implementation of RT mempool definitely could not satisfy the requirement of elastic resource usage. So, to support low-cost startup and dynamic memory consumption, we implement the dynamic mempool library by extending original RT mempool library in current DPDK. Our extension includes 4 main aspects of modifications. First of all, we don't preserve huge pages anymore, because preserved huge pages could not be used by host kernel even if they are not used by DPDK applications yet. So not preserving huge page is a premise of dynamic memory use. Then we implemented minimal startup allocation to reduce memory consumption of application initialization and also speed up the startup of application. The major extensions are dynamic grow and retrieve of mempool. With dynamic grow and retrieve ability, mempool could use memory elastically along with varying network loads. During the initialization, we would set not only the maximum size of mempool, but also set the initial size of mempool and the number of resource objects that would be allocated each time in dynamic mempool growth. Then we will not initialize the management structure such as the ring or stack with a size which could store maximum number of objects. Instead, we only allocate a minimal structure to store the initial objects, and then only the initial number of objects would be allocated and initiated. As shown in the graph, the startup stack and objects are relatively very small compared to the maximum stack, which is the original mempool would occupy. The next extension is dynamic growth. The populate or the growth of dynamic mempool is triggered automatically if the dequeue operation could not get enough free objects as required. If the number of already populated objects is smaller than the maximum number, the size of mempool could be grown. A specified number of new objects would be populated and initialized, and then inserted into the management ring or stack. If the ring or stack is not big enough to hold the all populated objects, a new bigger structure would be allocated to maintain them. After the dynamic growth, the dequeue operation would return with the new allocated objects, and all the above steps are transparent to the caller. So current libraries and drivers based on mempool library could still work without any modification. The dynamic memory allocation for management structure and populated objects is based on DPDK dynamic memory management or memseg, which is already supported by current DPDK versions. The last extension is the dynamic shrink. When the number of free objects is more than a preset threshold, the dynamic shrink would be triggered during the mempool enqueue operations. As we know, mempool would maintain the information of memchunks from which objects are allocated. So we extend the memchunk structure to record the number of total objects and currently free objects in it. In the first step of shrink, we will check if any memchunk is totally unused by comparing total and free object count in each memchunk. If we found some totally unused memchunks, the objects of these memchunks would be removed from mempool ring or stack, and then the memchunk would be removed from the chunk list of mempool and finally freed along with its related memzone. Here's a graph for the dynamic mempool shrink. So far, we have only supported dynamic shrink for stack-based mempool yet. As shown in the figure, objects of chunk 3 are moved to the top of object stack and then freed with a related memchunk. After the shrink, the remaining stack should still be compacted for further operations. By using dynamic mempool, we have reduced the startup footprint on time and memory significantly. Startup memory of DPDK v2 decreased to less than 100 megabytes from more than 1 gigabyte, and the startup time also decreased to 10% of the former. We also collected the statistics of the memory cost of DPDK v2 stacks in real online applications yet, and we found 85% of application instances only use less than 200 megabytes of memory, and only 2% of instances use more than 400 megabytes. Without dynamic mempool, we have to allocate at least 500 megabytes for each instances. Dynamic mempool could save at least half of memory consumption. As mentioned before, huge pages are not reserved anymore to support dynamic memory allocation. However, it leads to some other problems. At first, non-huge pages lead to performance degradation. In our cases, the performance of applications degraded by 2% to 3%. It's acceptable yet, but still evident. What's worse, when used with pass-through devices, it will lead to large amounts of non-compatible memory fragments. To avoid DMA attack, VFIO driver requires pinning memory allocated by DPDK, therefore affects memory compaction. As shown in the right figure, one unmovable 4K page would make 2 megabytes memory non-compatible even if it's almost free. In worst case, 100 megabytes of 4K pages may spread in 50 gigabytes physical memory, causing no huge pages could be allocated in this area, and it could cause no huge pages could be allocated for other applications who really need the huge page on the same host server. So to solve the problems, we use the transparent huge page feature in Linux kernel. By setting options of transparent huge pages in sysfs, kernel could allocate huge pages automatically for the application. When DPDK allocates memory dynamically, we add a call to memadvice to suggest kernel allocating huge pages for the allocated virtual address. However, transparent huge page is just a try-best function, and the Linux kernel does not guarantee it would always allocate huge pages as advised. So with this THP feature, the issue of non-compactable memory fragments could still exist in some time. So to solve the fragment issue better, we find another way to reduce the unmovable memory of DPDK. It's by using external memory API of DPDK. DPDK provides an experimental API named rt-malloc heap memory add to attach memory allocated outside of DPDK into the DPDK heap manager. With this API, we could generate two separate heaps in DPDK and use them for different purposes. In the internal heap allocated by DPDK itself, we could allocate objects and structures such as mbufs or RxJS queues that would be accessed by a device. Memory in the internal heap is still unmovable yet, and other data structures such as file descriptors and streams are allocated in external heap. So they are not pinned anymore and could be moved in future memory compaction. In most cases of our application instances, memory used by internal heap in DPDK v2 is much less than the external heap. By this way, we reduced unmovable memory of DPDK by about 90%. So far, we have introduced our extensions on dynamic mempool and memory management, but the work has not been all completed yet. Currently, the shrink method is still inefficient sometimes. It's possible that no mem chunk is totally free, while there are many free objects already. Therefore, the dynamic mempool couldn't shrink dynamically in this case. Up to now, we have an idea by adding a mechanism when shrinking, by triggering a mechanism to prevent mem chunks almost empty to be used anymore in the future. So normally, the objects of these chunks would be freed shortly, and by then, we would be able to retrieve them. Besides dynamic mempool, we also did some other works to make DPDK and DPDK v2 more cloud native. For instance, we tuned the static catch parameters affected by macros, such as RTE max error call, from 256 to 16 to reduce the size of some global arrays and structures. Also, we replaced RT-hash and RT-LPM library in the implementation of stream and root tables with linked list-based hash to reduce memory consumption, because the size of RT-hash and RT-LPM instances would be quite large. And we limited PCI scan time by mounting dedicated sysfs, which only include the files of device for current stack instance to speed up the PCI scan speed. And also, we shortened the TSC frequency detection time in initialization by taking a shorter sleep. With all these optimizations and customization, we could boot a TDK stack with virt.io in about 5 milliseconds and about 8 megabytes. At last, let's make a summary. Cloud-native environments requires DPDK to be more lightweight and elastic. So we implemented dynamic mempool as one of the solutions to support elastic memory usage and quick startup. By some optimizations and customizations on DPDK, including dynamic mempool we introduced today, TDK v2 has been adopted in dozens of key applications of Ant Group in cloud environment, and DPDK is proved to be a solid part for cloud-native network applications. Okay, that's all of my topic today. Thank you for listening. It seems I finished it a bit quicker, so we still have several minutes left to answer some questions. If you have any questions, you could type it in the chat box. Okay, I see the question. What is the additional cost if it needs to allocate a new mempool at runtime? If we want to allocate a new mempool at runtime, the additional cost is quite the same as the current mempool. I don't quite know if the question is asking the cost of time or cost of memory consumption. If we want to allocate a new mempool at runtime, both time cost and memory cost would be less than the current mempool implementation, I think. I see another question is, will it work with hardware-based memory allocator? I'm sorry, but I don't quite understand what is the hardware-based memory allocator. But I think if the hardware-based memory allocator could also be called in the runtime and the cost of its dynamic allocation is not that high, I think the dynamic mempool could also work with that. I don't find any reason that the type of allocator could affect the feature or the performance of this library. How about its performance, data, bandwidth, and latency? So the question is asking for the performance of TDK v2 or the dynamic mempool. We have not measured the performance of dynamic mempool very detailedly, because the allocation and shrink on dynamic mempool happened very rarely in the running of the stack. For the performance of TDK v2, I don't have accurate performance data with me, but actually we have introduced TDK v2 in last DPDK summit, and I remember in that In that topic, we have some data in the slides, and the performance of KDK-v2 is about 2 or 3 times better in some typical network loads comparing with the Linux kernel stack. I see another question in Chinese. 硬件协处理器用来分配内存块，我不是很理解这个问题啊。如果说方便的话，您可以那个线下或者邮件方式和我来交流一下这个问题，因为我不是太理解这个硬件协处理器用来分配内存块大概是一个什么情况。I see Jianfeng has asked, we have many places doing memory allocations. The way to allocating new mempool has to be done everywhere, which makes the code hard to maintain, and one place to allocate mbuf is in different drivers. Shall we do that change? Okay. It's just an answer. Okay, if there are not any more questions, my topic today is up to now. Thank you for listening.